the plan for today is that we are going to spend a little more time on the genus 1 case, and then we are going to do genus 2. So a short recap. We care about Lefschetz fibrations over some oriented surface. During this lecture, that oriented surface is always going to be S2, but doesn't have to be. So you can broaden your horizon and think about what happens when the base is torus or something else. And on the right-hand side, you could see, I hope, the torus and actually 12 curves inside. And so your first task, not during necessarily the lecture, but maybe after that, is to see if you can construct a Lefschetz fibration over the sphere with exactly these 12 vanishing cycles. So that means that over this point, I have an honest torus, that torus, exactly this torus. And on that torus, there are various curves, 12 of them. And they are representing for you these so-called vanishing cycles, which means that if I take this point and try to approach one of the, I don't know, red points, or maybe, yeah. Going close, then you always have a torus, and so you can sort of identify these torus with each other. But at this point, there is something funny happening. You might remember what happening is a singularity, which means that one of the circles will degenerate. The picture might be that originally we have this nice torus, but I'm preparing for the possibility that there is some singularity happening. And what's happening is that when you go from here to there is always a torus, but somehow you should think about these circles getting smaller and smaller in this family, while at the degeneration, what's happening is that this whole circle shrinks to a point. And instead of a circle, we just get a dot. So we talked a little bit about monodromies. What happens if I would try to test what's going on by, instead of going straight to the source, actually go around and come back. Now we have a one-parameter family of tori's coming back, and there's an automorphism. This automorphism was, I claimed, always a right-handed Dane twist. So it means that nearby this circle, things try to twist to the right direction until they completely go around. And this is a monodromy. In case of genus 1, everything is so simple. You can just look at the action on the first homology that will give you a matrix, and this matrix actually tells you everything about this monodromy. So you can pretend that we are studying 2x2 matrices, SL to Z, and in fact, this is exactly what we are doing. So what is the homework? Is to try to distribute these 12 curves so that you get an actual Lefschetz fibration. What do I mean? Each of these things represent you an action on the torus to itself. So I guess phi A1 is a map like that when you do Dane twist on A1. Phi A2 is another very, very similar looking map, right? Because it's isotopic to each other. In fact, these two things actually do commute. I could do first A1 and then A2, or A2 and A1. It's going to be the same. But when they do intersect, they no longer commute. So why I told you that there will be a Lefschetz fibration with exactly these 12 curves, but I forgot to tell you deliberately what is the order in which you have to do this. And the claim is that there will be an order in which you get the identity. Meaning that if I list these things, I could start actually with A1, A2, A3, but then you have to figure out what is the next. Is it B, C, D? And in what order do you have to do this so that when you multiply all of these things together, you get the identity? But the claim is that it's possible to do this, And we could have a Lefschetz fibration with exactly this kind of vanishing circles. So this is your task. If you are interested in it, it's not too hard. In fact, we are really talking about matrices in some sense right now. Very soon we are going to talk about more complicated things. But I would like to mention that there are different approaches here. So one is this brute force approach that you test your monodromies. You have some test circle. Doesn't even have to be isotopic to any one of these circles. So choose your favorite circle in the torus. Apply all these dainties together. And if you do get the identity, that means that you have to get back the same circle up to an isotopy. Is that okay? Is that enough? Not really. But if you have sufficiently many test circles, in this case at least 2 of these things that intersect each other once, then you can, if it's true that the isotopies eventually, or these dainties, multiplying together. So what are we doing? We are taking the first daintwist, and then we take the second daintwist, and the third daintwist, and compose all of this together. And what we have to prove is that we get an identity. So this is a very straightforward method. Even works in higher genus with some modifications. It's called the Alexander method. So you can either rediscover it, think about how many test curves do I need to make sure that I get the identity, or look it up. There is a really nice book by Farb and Margolid called the Primary Mapping Class Group, which is a long book, but there is a lot of information about the mapping class group. So my point is that there are different approaches, and there are these brute force approaches. I already told you there is a relation. All you have to do is to check it. But you could maybe be wondering where these relations really come from, or is there a way to, instead of just thinking about very hard how on earth I could put 12 circles on the torus, just find these circles by another method. So the good news is that algebraic geometry gives us all kinds of interesting four manifolds, and some of them come with nice Lefschetz fibrations, and we could just study them. And instead of trying to guess what these curves are, we can actually find these curves. So I don't want to spend maybe too much time on the genus equal to 1 case, and maybe this is something that at least partially discussed in the problem sessions as well, but I think it's such a fascinating example that I would like to say a little bit about this. So the approach is that we are going to take today and also next time is that there are some beautiful algebraic geometric constructions that do give us relations. Let's try to understand some of them at least. So the thing I would like to concentrate on now, how do we get Lefschetz fibrations, is to start with CP2 and inside look at two very special genus 3, so degree 3 equations. So I'm going to write down this is a homogeneous equation now in CP2. It gives you a complex curve. You can actually prove that this is a genus 1 curve. And I'm going to write down another equation, which is xyz equals 0. Also homogeneous, also degree 3. So you should maybe, you could hope that this is also going to be a genus 1 curve, but it will not be. You can easily see what are the solutions. Either x is 0, or y is 0, or z is 0, which means that you have actually 3 hyperplanes inside. So the solution space here is more like 3 things intersecting. Why this is actually a genus 1 curve. How do you prove it? You can compute its Euler characteristic. You can prove it's non-singular. So I have 2 equations in CP2, and this solution spaces actually do intersect. So this is, I'm going to say things, but your homework, or I guess your problem, if you want to think about this more, is to fill in the gaps. So, I mean, clearly very easy would be to solve the intersection point between these things. X is 0, okay. But then x is 0, so y cubed plus z cubed is equal to 0 means we are in CP2, so both of these should be non-zero. So I could rescale, so y could be 1, and then I have to solve z cubed equals -1. I will have 3 solutions. So all in all, you will have exactly 9 intersection points. Do I really want to draw this? Yes, I do. 6, and so something like this would be the picture inside CP2. I really don't mind questions. So if you have questions, you can ask them now or later. So this is, I guess, our image. This is our understanding of what happens inside CP2. And we don't have a fibration yet. In fact, the only thing we have is one single genus 1 curve inside, so one single torus that we see. But as it turns out, you can play with this and write down. So András already mentioned something like this with a slightly different equations, but let's just do this very quickly. So I could fix lambda, which is pair of complex numbers. Not both of them are 0. So I really view this as lying in CP1. And what I'm going to do is multiply lambda 1 times the first equation plus lambda 2 times the second equation. And now I'm looking at the solution space of this equation inside CP2. Is that okay? So if I would multiply against the homogeneous degree C equations, if I multiply both of them with, say, 5, I will get the same solution space. Or with any complex number, I will get the same solution space, non-zero complex number. So this is why our parameter is really corresponds to an element in CP1, this pair lambda 1, lambda 2 modulo reparametrization, multiplying the same complex number. Okay, so it means I have a bunch of solutions, one for each such lambda, right? And then the rest is very easy. So imagine I have a generic point in CP2. I plug in the first equation and I get non-zero. I plug in the second equation, I also get non-zero. So I get one number here, non-zero, and another number. I can certainly solve for lambda 1 and lambda 2 so that it actually is 0. So which means that if I have a generic point, this is my CP2, I have 9 special points. These are the intersections. These are 9 special points. But apart from these 9 points, 9. So apart from the 9 point, every point will be able to decide what is the corresponding lambda 1 and lambda 2. Okay? But there are some special points. These 9 points are special. Special because both for them both this equation vanishes and that equation also vanishes. So no matter what lambda 1 and lambda 2 is, these points will also be on the corresponding lambda curve. So what we do here is I have CP2, and it's broken up to some curves like this, going through all the 9 points, right? This is one of the, I guess, sigma lambda, if you really like. This is going to be in general a torus, but not all the time. And what we have is they're sweeping at CP2 by lots of things. I claim most of them are actually toris. But they are not disjoint, unfortunately, because all of these things go through the same 9 point. So I don't really have a map from CP2 to CP1, right? Remember, what we want to do is to study Lefschetz fibrations, which is a map from R space to CP1. In this case, it would be holomorphic. We don't really care about that so much, but we care about the smooth things. But right now, we don't have it. However, you might recall from András's lecture, there is something called the blow-up, which means, let's just recap this, that I replace locally C2 with something else. What I do is I take a subspace of CP2 cross CP1 and have a map to C2. And this is actually very easy to find this subspace because it corresponds to two things, a vector in C2 and a line in C2. So call this V and I don't know, X for line, not the best notation. And the subset that you are looking at here is that the vector lies in X, if that makes sense. So elements is CP1, this is C2, can be viewed as complex lines through the origin. And so this is X. And I'm using at special vectors V's in C2 that correspondently line in this line. So this is a subset, an interesting subset here. Of course, I could forget about X, and I have a map to C2. What happens, though, is that if the vector is non-zero, then there's a unique line going through that. So for non-zero vectors, here, there will be a unique point up there, which is the same vector and the line that goes through it. The origin is special because the origin as a vector goes through lies in every line, right? So over the origin, we get a CP1 verse of things. And this is what András said, delete the point, replace it with a CP1, which is a sphere. And we are doing exactly this kind of operations here. We have all these different things, all going through the same kind of point, right? But what happens is that if you look at very carefully to these intersection points, I delete these intersection points, but I replace the point with all the different complex tangencies. I do this operation of replacing C2 with the preimage. And what that does is that although we used to have these different intersections at these points, now they are no longer intersecting because here I replace that point with these complex tangencies, and I replace that point lying on the red things with complex tangencies. And so we made a really drastic change. I had CP2, but I changed CP2 because I blew up 9 times. So this is called the blow-up operation, and in terms of the manifold is that we have CP2 blown up 9 times. And now we have an actual map to CP1. What is the map? Well, for a generic point, associate to it lambda. And for some of these special points, we replace things with the complex tangencies. So what you have here is now an honest map, well-defined continuous map. It's even holomorphic. And it also has sections. In fact, it has 9 sections. All the CP1s that we get is sort of exceptional spheres that you do the blow-up will map down to the parameter space. Any questions? Okay. Yes?
So, for one of the points that's lying in one of your 9 copies of CP2 bar, where did they go to in CP1 under this?
Right. So what is this local model? That I have a map to C2, right? But, of course, I also have a map to the second factor, right? CP1. So basically, you could use that map to guys. Okay, so this you can do all the time. You need a polynomial and not a polynomial, but you can do it also in a very special case when you do exactly for these polynomials. And my suggestion is to actually do this. So it's very explicit. And what are the obvious questions? I have these kind of equations, depends on lambda. And the question is, for which kind of lambdas would we get a singular solution, right? So usually you should accept a torus, but finally many times you won't get a torus, unfortunately. In fact, you already see one example, this example, that corresponds to, I guess, lambda 1 being 0 and lambda 2, 1. So for the point 0, 1, we get this thing, which strictly speaking is slightly more complicated than the things we have discussed before, because instead of one circle degenerating, now it's basically 3 circles degenerating. So the right picture here is that we have a torus and in fact the way to get 3 spheres out of one torus is that you do more than one degeneration. In fact, you do exactly 3 degenerations. And I'm going to erase this. So apparently, these things are taped for better or worse, so you can look up these equations later. So the singular thing, it actually looks like this, that we have three spheres. So this doesn't look like the original solution space, but in fact it's the same thing. We have one sphere, we have another sphere, and we have a third sphere, and they intersect in 3 different points. It just looks slightly different from this point of view. So if you really want to go through this kind of example, and I highly recommend you do, you will see that there will be only a few singular points down in CP1, and it all look like exactly the same, namely that instead of 12 singular values, now we just have 4 singular values. Find lambdas for which this happens. This is one of the examples when this happens, but you should be able to find the other. And it means that in S2, we have these 4 singular values when simultaneously 3 things degenerate. So you can see now in this picture that one of the things would be the A1, A2, A3 degenerating, and you could see the others as well. You will see 4 different directions, and in each case you have 3 circles degenerating. And if that's the only thing you care about, namely you wanted to understand what manifold we got and what are the vanishing cycle, we have it. If you want to go deeper, meaning, for example, you want to understand the sections of these fibrations, these CP1s, the exceptional spheres as well, not from the algebraic geometric point of view, but from this picturesque point of view of vanishing cycles, then you can wonder where on earth are the spheres, right? There are 9 spheres, and apparently these 9 spheres intersect the torus in 9 points. And I can help you out. So these will be the 9 points when they intersect. So a few things about why do I care about this example, or why you should maybe also care about these and similar examples. So if you only study genus or Lefschetz fibrations, you maybe don't need so much, although even in that case, you can do rational blowdowns. Rational blowdowns require lots of spheres. Now we understand, now we have lots of spheres in this singularity, so you can maybe employ them to do new constructions, namely take E1, blow it up some more, take out some configurations, glue back something else. So even if you just want to study the elliptic fibrations and modify it, this might be useful. It's even more useful if you actually think about this picture as not lying in the torus, but lying in the torus with 9 holes inside. Is that okay? So this is a picture that makes sense also if I take my torus and make 9 holes on it. Yes.
So if we just take the monodromy of this guy,
Yes.
we get A1, A2, A3. Is it just
Yes.
power? Okay.
Yeah. Yes, you had A1, A2, A3. But you have, I guess, 3 other things, and you get B1, B2, B3. This is A, A's, B's, and is it C? Is it D? That is like, at least let me give you, let's have a little mystery. But that is like part of actually making sure that we get a relation. Okay? But yes, it will be A1, A2, A3 times.
Okay, I see. Not exactly D1, B2. Okay.
No,
Yeah.
the next is not going to be B. It will be C or D, and this is your task to realize. Okay? But in the torus, in the closed torus, this is all we need. But if you want to think about the torus with some holes in it, turns out there is a version of the mapping class group with either puncturing or really making boundaries. And now we are doing the case when we have boundaries. And that means that, that the automorphisms we are studying will fix the boundary components as well. Okay?
I'm still confused because if you have something like that, if you have some singular like that, it looks like the monodromy is always something to the power of 3. So that's okay.
That's right. This monodromy is using A1, A2, A3. This monodromy will be B1, B2, B3, right?
But the other 2 singular fibers are not like that.
Now, they also, okay, so, okay, I can spoil the, spoil the suspense. It will be exactly like this.
Oh, okay, but still it's some power of 3.
Right, so you have an element which is a cube of something times another model which is a cube of something else, and so you have A cube, B cube, C cube, A cube, C cube, B cube, D cube equals to 1 on the mapping class group. This is if I'm not deleting these points. However, if I actually do care about sections or I want to do something deeper, then I care about these circles as well. And now you can immediately realize that A1 is actually not isotopic to A2 anymore. Okay? And now it matters that I use A1, A2, and A3. The order still doesn't matter. They still commute. But between A1 times A2 is the same as A2 times A1. But now, it does matter exactly where these things are. So there is a version of the mapping class group with holes. And the statement is that if you do the same Dane twists along these curves, now you no longer get the identity, but you get something which is called boundary Dane twists. Now you have, so we used to have basically 2 interesting curves in the torus, like A and B, right? But now we have more, and now we have also new kind of things, which is twisting along these circles. So remember, Dane twist, go to the circle, turn right, go completely around once, and then go forward, right? So now we have also this so-called boundary Dane twist. So the statement is that something like A1, A2, A3, B1, sorry, C1, C2, C3. B1, B2, B3, D1, D2, D3 is equal to, well, I have these delta I circles, and they also give us right-handed Dane twist, so the statement is delta 1, delta 2, delta 3, delta 9. Which is a famous relation, the 9-hole torus relation. And so I'm spending more time on this than I thought, but fine. But so this is something So there are various tricks you want to know about if you want to look at Lefschetz fibrations in general. And there are various nice identities that you can always use. This is one of those really nice identities. So if you care only about genus 1 Lefschetz fibrations, that it just tells you that you have 9 sections with self-intersection -1. The -1 comes from this being that these Dane twists are rotating ones. But this is a relation that takes place on the torus with exactly 9 holes. I'm not going to draw the 9 holes, but you have 9 holes. What it means is that this works in this submanifold. So suppose you want to get a relation instead of genus 1, genus 10. Okay? Well, what you could do is just try to extend these things to the larger surface and realize that now you have a new relation in these larger things with some kind of Dane twist coming from here. Or you don't want that, you do something else that also works. So anytime you have these Dane twist relations with things with boundary, you can promote them to closed relations, which means that you could use them for a different purpose later on to get some interesting other Lefschetz fibrations for a higher genus thing. Why do we care about Lefschetz? Yes?
So when you do it like that, then I'm a little bit confused whether the positivity of the Dane twist would be preserved. Because in the relations that you were describing for getting Lefschetz fibrations, it was necessary that Dane twists are positive.
You are right. So what we get is an identity in the mapping class group. And how you use them, it's up to you. But you can use various tricks to use these things. So as always, what you have to do is to start somewhere and build up your I guess, book of tricks or your favorite techniques and what can we do with these techniques. So all I'm saying right now is that algebraic geometry is useful, and even if you didn't know about these 9-hole torus relations, you can actually find it by working out this example, and that will be all. Okay. And so what I planned for these lectures is to go through one of these big hits of interesting relations in the mapping class group or interesting Seifert fibered manifolds and see whether we can peek under the hood and understand these relations. Okay, so I promised genus 2, so let's start with genus 2. There are 2 methods. One is somebody tells you a relation and you check it. And then the other method is that you find the relation by yourself. We have 10 minutes, so it's probably enough to somebody tells you a relation and you go home and check it. So this is what we are going to do. But we want to have a handle on genus 2 surfaces a little bit. And the trick we are going to use is that if I have a genus 2 curve, then I can rotate around this line with 180 degrees, and this is an involution, and I could divide with that involution. That involution is exactly 6 fixed points. So what you get at the end is the quotient with 6 special points. The quotient is the sphere. So I like to think about the genus 2 surface, and I hope you will appreciate this point of view. In this and the next lecture, is that I take the sphere with 6 points, your choice which 6, and then you do something called a double branch cover. Is that okay? which in very mundane way you can understand by taking y squared equal to x minus alpha 1. Maybe save time. Product from I equal to 1 to 6, x minus alpha I, when I deliberately choose different alpha i's for all 6. So I have 6 alphas. And yes, right now it seems like it's in C, and it is, but so that you can extend that to CP1. You can see that a very large circle, what happens with that, it will be so what happens here is that for any point in C, any generic point in C, I have 2 solutions for y, except for a few very special points, namely when x is equal to alpha I, then I get just 1 point downstairs and 1 point upstairs. So this is something which is a degree 2 map down to the sphere, and is branched along these special points. And this gives you another model for the genus 2 curve if you understand what happens at infinity and add 2 more points at infinity. So one homework, if you have never seen this before, make sure that you see why to get the genus 2 surface if you add 2 more points at infinity. But nevertheless, this is going to be our standard model for a genus 2 surface. I give you 6 points, doesn't matter where they are right now. And I just do the double branch cover, and that gives us a genus 2 surface. And let me make sure that we have the correct. Yep. So I have to give you 4 pictures and then explain it, and this will be all for today, I guess. So this is going to be A1. What do I mean? I take the double branch cover of the sphere with these 6 points, and I take this line. It is a line now, but in the double branch cover, it will become 2 lines meeting at 2 points, so it is a circle. Okay? And this is going to be surprisingly symmetric. So this is going to be A2. For those of you who know what the Matsumoto relation is, this is going to be the Matsumoto relation, maybe in a disguise, but nevertheless. And what else is there? There I could also do this, and this is A3. And so right now we have 3 curves, and I hope you can easily see that these are homologically non-trivial curves in the genus 2 surface, or if not, then try to see another curve that it intersects once. For example, take this curve, then they will intersect once. So, but I need another curve, last one, and that would be that curve. And this is B. Note that the 6 points are fixed throughout all of these. I want a fixed genus 2 curve that is unchanged. Only the curve will change. But what's special about this curve, and it looks different from the others, it seems like it's a circle down in the sphere, true, but there is a double cover of it in the genus 2 surface. You can see that since inside there are odd number of points, 3 in this case, then this is actually in the double, the cover of this is a connected double cover. So for this one circle, there's a connected circle up in the genus 2 surface. And so this is this B. In a slightly different notation, remember already erased it, bad idea, but you have these 3 altogether 6 points, right? And in that picture, you might think about B as this. So right now it looks like this is done in the sphere, and they are, but I really think about the the image is in the pre-image is in the double branch cover. So I really think about these curves lying in the genus 2 surface. And the identity, I guess this means I'm taking the corresponding right-handed Dane twists and multiplying them together, right? And I guess one question I have for you is, what is this? So you can think about this is going to be a monodromy on the genus 2 surface, right? And you could, if you want, really try to understand what this is. And it's not going to be the identity, as it turns out, but the square of it will be the identity. So this is a relation. And this is a relation that you could either look up Matsumoto's relation and try to prove it or follow the argument, or plan B, find the corresponding genus 2 fibration and make sure that these are the vanishing cycles and prove it that way. Or third option, try to just slowly prove this. We have 2 more minutes, so I can try to tell you how to do this in a relatively painless way, and it's something you can really do. So the only thing, we know what to do. We could do this in the hard way of lifting up these curves to the genus 2 surface, right? And do the corresponding Dane twist upstairs in the genus 2 surface and hope for the best. So that is one method. There is a slight shortcut, which I like, and maybe I can share, which is we have this really nice involution, which really simplifies our life. Instead of working in the genus 2 surface, we work in the sphere. So can we understand these relations in the sphere? Turns out, yes, we can with a little work. So the only thing is left to understand is what happens when I have some curve and would like to understand the effect of a Dane twist along one of these things. Okay? So think about what I said about test curves, right? So this is a curve, as it turns out, in the genus 2 surface, right? And we could see what happens when I use all these different things one after the other one, okay? And I can try to use, so I could cheat and look at an even simpler example, like I could use this for today and see what happens if I would do Dane twist on this guy, or I take this curve and apply A1 to it. Nothing, because they don't intersect. So I did the first step. I did A1. Now I have to do A2, which is I have this curve. And now, remember, our goal is really to do this in the cover, right? But turns out we can imitate what happened in the cover. We can follow it downstairs. So what was the thing to do above? It was a right-handed Dane twist. So it turns out that is going to be very nicely just push this to the right, and then I get this. And now, isotope it. So now epsilon maps to this curve. Is that okay? So now I do the next step, which is use the right-handed Dane twist on that curve, and moving to the right, I would get this. And the last one, this is where my image is. It just doesn't intersect this at all, doesn't do anything. So I guess we have seen that if I take this curve and apply this A1, A2, A3, and B to it, then unfortunately, or fortunately, we don't get the same curve, but we get a very similar curve, we get this. Okay? Now, very quickly, turns out there are only finitely many computations you have to do. Think about why. The key idea is that if I have a bunch of curves that decomposes the genus to surface, these curves should intersect each other once and some other properties. Think about what those properties are. But basically, it's enough to only check this for a few curves, 3 in this case, because it's very symmetric. And I could check it for epsilon 1, epsilon 2, and epsilon 3, but it's very symmetric, so you can also check it for more if you really want. And turns out, if you really wanted to understand the effect of this, then you can just have to look at these curves. Very quickly, not all the computation with that simple. So very quickly, if I had a curve that intersected this maybe once, that's the simplest case, then it will greatly change it. But it will change it in a very predictable way. You go to the right, then you go back, and then you go forward. So this will be remember, Dane twist happens upstairs. You have to think about, how can I understand this downstairs? And it turns out, yes, you can actually understand this. So if you do this on one of these curves, then there is this go to the right, go to the left, go forward kind of weaving you have to do. Slightly trickier to see what happens for these curves. This is a circle, but it's a circle upstairs which double covers this. And the statement, again, take it as an exercise, that if I wanted to understand what happens if I use right-handed Dane twist on this curve, and for one of these epsilons you actually need to use this, then you are doing the thing like, right-handed, right? Turns out that is not enough. You do have to circle around once more and then go forward. So there are these really simple sort of calculus of how to work with double branch covers and use the Dane twist, but if you employ them, then what you could see is that if I don't square, then I get a rotation by 180 degrees in this picture, but if I square, then I get the identity. So that is Matsumoto's identity for you. Why should we care? I tell you next time. I guess we are out of time.